Hello my dear friends. In this video we'll learn about torque. Main idea is to be able to see what is the difference between torque and force, understand how to solve simple torque problems, and realizing that gravity actually can apply a torque. Torque is simply defined as the rotational effect of forces. So if there's a force, we have force, we know that. A force may be able to or may not be able to rotate an object. If it's able to rotate an object, it has a torque. This figure here nicely showing if we are trying to open a door. This is the hinge of the door here. We all know that we have to apply a force. The best way to do that is to apply a force at the edge of the door over here and perpendicular to it. And if we apply the force in this direction, it would be very inefficient to open the door. Or if we apply it very close to the hinge, it would be very inefficient as well. If we apply a force in this direction, we are simply pushing along the door towards the hinge. We won't be able to open it at all. That's a very good way of seeing what is torque. So if a force is able to apply a rotation, it has a torque. And torque is defined as the force, perpendicular component of force times the distance r, like in this equation here, and distance r being distance to the point of rotation, which is the hinge in this case. So if I'm looking at forces 1, 2, and 3, this would be R for them. If I'm looking at force 4, this would be R for it. What F perpendicular means is we are looking at the component of F that is perpendicular to that R that we defined. And the force F1 is already perpendicular to it, as you see. So if I have that, I already have perpendicular force. But if I have F3, for example, what I'm going to do is I define an angle. It's defined as phi. This is a Greek letter in the book, so I'm going to stick with phi. But it's an angle. I can give it any name. And F perpendicular will be F3 times sine phi here. And in this case, I'm looking at the perpendicular component to R. Notice this is y component if I set my xy directions here. And I know what we know y component was sine. So it's kind of the same thing applied and turned around. So if I have F3, it will have a perpendicular component calculated this way, and I'm going to input that here. If I have F1, it's already perpendicular, or F4. For F2, it's parallel to R. We already logically decided it has no torque. It has no torque because it can't rotate the door. Physically, right? Mathematically, if I look at the sine, apply the perpendicular component equation, I will see that sine 0 is 0. So I'll get a 0 perpendicular component. Direction of torque will decide dependent on the rotational directions. We'll get to that. But actually, physical direction of torque is found using the rotational direction with what we call a right-hand rule for torque. If I grab the rotating object, turning my fingers along the rotational direction, logically I define the rotational direction, and I do this, open my thumb will always be showing the direction of torque, which we will use the letter tau. It's again a Greek letter. We love Greeks, so we use their letter all the time. So this equation will be what we are sticking with. Torque is equal to the distance to the rotational point, we generally call pivot point, right? Times the component of force perpendicular to R. And this will always be R times F times sine phi. And phi being the angle between F and R. So I define my R direction, or R, and then I define my F. I'm putting random directions here. If this is R, this is F. Phi will be the angle between them. Let me make my phi better here. Phi is simply 0 with a line on it. That's torque. Unit of it would be Newton times meter. Why? Because the distance, SI unit, is meter. Force is Newton, so Newton times meter. There is no special name for torque's unit. We'll just stick with Newton times meter. This figure is summarizing what we already talked about. If we have a force with an angle phi with the distance to pivot point, we find its perpendicular component, and that perpendicular component is F times sine phi always, and torque is equal to R times F perpendicular, and then we put R F sine phi. There could be some situations, this is the same thing turned around. In the first case, I look at R and angle between F and R. I could also take the extension of F and draw a perpendicular line to the pivot point. That would give me what I call R perpendicular. It will give me the same result, so I can always stick with this equation here. But again, in some pictures, in some figures, in some problems, it's easier to just draw the extension of force. You can maybe see what R perpendicular is and just directly calculate from there. Other than you won't be able to you won't be needing to use this. But we can also turn this around and say torque is equal to perpendicular direction to the pivot point times the force. And each gives me the same equation, RF sine phi. Here's an example. Ryan is trying to open a stock door. He pushes it at a point 0.75 meters from the hinges. So we have hinge here. This would be my pivot point. We should always define a pivot point, meaning around which my object, which is the door in this case, will rotate. We will be focusing on the direction of rotation more later as well, but logically also define the direction of rotation, which is counterclockwise in this picture. CCW is counterclockwise. All right. Not necessary in this, but I'm preparing you for the future. So he applies a force of 240 Newton, 0.75 meters away from the hinge pivot point, directed 20 degrees away from being perpendicular. This is a weird definition, but they showed it in the picture, so it's easy to see. It's not perpendicular, but 20 degrees away from it. Right away when I hear this, remember folks, we always think about as we read the question what we should do, right? What I would need to do. I would need this angle, phi we called it, always the angle between R and F. Notice how I can extend my R to find that angle properly. Now this little angle here is given 20 degrees. Let me pick a different color here. And it's clear that this angle is 90 degrees, right? I'm going to draw it on this side to help you guys see and avoid too much clutter here, but 90 degrees. So phi is equal to 90 minus 20. So I find that angle right away if I can put it there, 70 degrees, because I will need it, I know, for my torque. All right. What is the torque Ryan exerts? Torque, I'm going to jump into directly this equation. R times F perpendicular, we will be mostly using this. RF sine of phi, I inputted my phi here, 70 degrees. And that is it. My R is 0.75 meters, given in SI units, no conversion needed. My force is 225 times 53 Newton. I don't know why I did this. No, it's not that. It's 240 Newton. So let's change that. 240 Newton. I do this sometimes. And I'll multiply all these. I'm going to redo this because, oh, the number at the end is correct. I already calculated it correct here. 240 times sine 70 times 0.75 is, guess what, this number here. But by mistake, I put it here as this. Probably I changed it from this number to there, and I forgot to change it in here. But no problem, here is 240. I'm crossing this out and putting 240 Newton. When you do the multiplication, you'll find 169.14 Newton meters as the torque. And again, I decided the rotation direction logically to be counterclockwise. How he can increase the torque is the part B of this question. Logically, I can increase the torque by applying a larger force, right? So by increasing the force, that's one option. Or I can apply it from a farther away point, each of which will make one of these values larger. So apply it a farther distance from where? From the pivot point around which my object door is rotated. So from the pivot. And what else I can do? I can actually apply my force perpendicular, so I can actually increase the angle phi towards 90 degrees. So apply F at 90 degree, right? I can apply the same force at 90 degree would give me the maximum torque. Then F, not only component of F, but all of F would be working on the torque. So that's the idea of torque. This page is simply thinking about what we talked about already, comparing torques for different situations. So we'll do this slowly. If you start compare what we have top here is kind of a different question than what we have down there, but all the same idea. So question 1, compare the torques in here. I'm going to call them torque 1, torque 2, torque 3. I see here torque 3 is already 0. We're trying to open a door, pushing the door along the door towards the hinge point or the pivot point will not cause any rotation, so no torque. Applying the same force at an angle will always be smaller, so this guy is small or smaller than tau 1. Okay, I'm gonna rewrite that. Smaller than tau 1. And tau 1 would be larger. I'm applying the same force, 90 degree. That's the best case scenario. So as I write down my comparison, it should be tau 1 is larger than tau 2 is larger than tau 3, which is 0. Or it could be tau 3 smaller than tau 2 smaller than tau 1. Similar situation here. This guy would be larger. This guy would be a little bit smaller. And tau 3 is almost 0. I can guess that would be the smallest one. For a perfect comparison, I would need to know the values. But I know F is the same value here. This guy is almost parallel, means it's close to 0. So it's still the smaller. So I would have the same comparison. Tau 1 is larger than tau 2. Larger than tau 3. Tau 2 is smaller, notice here, because it's applied to a closer distance. If this was R1, R2 is smaller, and tau 3 is almost 0 because F is almost parallel to the door. So some logical questions might appear in this format. As we define the direction of torque, again, we have a right-hand rule to find the real physical direction of torque. And to do that, we will define the direction of rotation, shown in this figure, to be looking from this side to be counterclockwise. And then we put our hand, grab what the object we have that is rotating, and roll our fingers along the direction of rotation. And our thumb will be showing the direction of tau, torque. This is physical direction, but we will not really worry about that too much. We will only look at if an object is rotating clockwise or counterclockwise. And that's pretty much easy to see with logic. And if an object is rotating counterclockwise, conventional acceptance is that torque is positive. So we'll stick with that. If we decide that the object is rotating clockwise, or if force is causing an object to rotate counterclockwise, it has positive torque. If it's rotating clockwise, it has negative torque. Needless to say, folks, torque is a vector. Why? Because it has a direction, and here's how I can find it. This figure here from the book is nicely explaining the forces applied to the same point at different positions, different directions, and how they would cause the torque. The first one here, for example, zero torque is pushing towards the pivot point. No rotation will be caused by that force. This one would have the maximum torque because it's applied perpendicular to the distance r. Let us show the distance r here. For clarity, it's kind of obvious. This would be the r distance. And this force would have applied torque, yes, rotate the object, but would be smaller than that. And this also would be zero torque. Here we have a torque by this force, again still smaller than that. If the angles are the same, by the way, it would be same magnitude of torque for this force and that force. And this force would also apply a torque. And it would be also maximum torque. Alright, because it also is perpendicular to R. Now let's look at the directions. We looked at the magnitude comparison. This we will do by logic. Always imagine it's you who are applying this force and trying to rotate the object here. If I apply this force, maybe I'm going to call them F1, F2, F3, and tau 1, tau 2, tau 3, and so on for clarity. So 6 different ways of applying the same force. Logically, this force here, tau 2, applies and generates a tau 2 torque would be counterclockwise. Right, rotating the object counterclockwise. What is that direction? Positive. Torque 3 would also be counterclockwise logically, so also positive. If I can't see that, I look at its perpendicular component. F3 perpendicular would be that. So it's the same direction as 2. That would help me understand that it should also be rotating counterclockwise. So positive. Torque 4 is 0. We decided no rotation. Torque 1 is 0. No rotation. Torque 5 would be this direction. Again, it might not be easy to see, but I look at its perpendicular component. It would be the same as F3 here. So it would also rotate. Then it's easy to see that it should rotate clockwise, which is negative direction. So as we have, you might have more than one forces applied and more than different torques applied to an object, and we might need to calculate total torque. What we're going to do is we're going to define rotation direction, take counterclockwise positive, clockwise negative, and add all the torques as vectors to decide what is the final torque. Again, torque is a vector. We will add them as vectors, but it's not going to be a hard matter after we decide what direction each force rotates and direction of torques. For example, here we have a wheel and different forces applied to, and we're going to decide the direction of torques for all. and this is the pivot point. We are rotating it about this point. All right. Starting from F1. Again, I'm assuming I'm applying this force, imagining. Take a fidget spinner, hold it in your hand, hold it in the middle, and apply these forces to see this clearly. It really helps. So F1 will apply a torque 1 that will be clockwise, so torque 1 will be negative. First we'll decide that. Then I can calculate that torque 1, F1 times R, distance to here. But this case we're only deciding directions. Torque by the force on the axle would be 0 because it's applied to pivot point. No force applies a torque if it's applied to pivot point. And logically we can't rotate the object, so no torque. So if axle here, force applied by the axle, 0 torque. F2 over here would rotate this way. What is this way? Counterclockwise. So torque 2 is positive. F3 would rotate also this way, counterclockwise. Torque 3 is also positive. And the last one is F4, would rotate in this direction. Again, I'm all deciding these logically. Imagine this, if you have a fidget spinner, have it, hold it in the middle, apply all these forces to see the directions. Torque 4 is also negative because it rotates counterclockwise. Then we will find all the torques applying F perpendicular times R. We'll do some examples on that later on. Here's an example of a torque applied to a biological situation. We always apply this torque to our ankle actually. Figure below shows the ankle joint and Achilles tendon attached to the heel at point P. So point P here, a tendon applies a force and it helps us actually walk. The tendon exerts a force of magnitude 720 Newton. I'm going to try to show that. Let me choose a straight line here. So there's a force applied here by the tendon, and that force is equal to 720 Newton. It's shown in here. Determine the magnitude and direction of the torque of this force about the ankle joint here. So there's a distance to the ankle joint, and I'm imagining I am the force applied and rotating this feet. It would be this direction. So torque will be negative. Why? It's clockwise. I decided that. And I am asked to calculate it. I'm going to calculate its magnitude and I'm going to know that it's negative. So this is the rotational direction. So negative torque means it is rotating the related object clockwise. The ankle joint is located 3.6 centimeters away. That's R. R is equal to 3.6 centimeters. Divided by 100 will be meters, so 0.036 meters. The question doesn't mention, but it shows the angle here. I was taking measures of the angle given. It's given in the figure here. This angle is given as 55. But that's not the angle I am looking for. Excuse me. I am looking for the angle between F and R. This angle here. I'm going to call it phi. But looking at this little triangle here, I don't want to really clutter this figure. But we have a perpendicular degree here, 55. This angle phi can be found using the idea that total internal angles adds up to 180. So this angle, 55 plus phi, should be 90 because the other angle is 90. We can find phi from there. Phi plus 55 is equal to 90. So phi is equal to 90 minus 55, which is 35 degrees. After I find that, I'm gonna calculate my tau as r times f perpendicular. I'm skipping that, I'll always say rf sine phi if I have a phi. If f is perpendicular, it will be simply r times f. Because you guys like this better. Distance to pivot point 0.036 meters. F is 720 Newton times sine, my phi is 35 degrees. And after I do that, I will get a value of tau as, let me see if I have that here. It's 14.87. And the unit is Newton times meter. Direction, if I'm asked to provide the direction, it's negative. So this is magnitude, and direction is negative, meaning it's clockwise. That's what torque is. Torque, gravity applies as a torque, which is mainly about how we can maintain balance. We can think in terms of a person or any irregular object has each a small part or molecule particle is applied a gravitational force, and we can assume these are all centered around a center point, which is around our belly actually, and we can show all the weight in there to think about gravitational torque for an object. And there's an easy way to decide. That's called, by the way, center of gravity. Okay, center of gravity. And each object has a center of gravity. We can use torque to calculate it, we'll get to that. But for symmetrical objects or any object, we can define about where the center of gravity is by just hanging them. For example, if I have a ruler and I hold it from the edge, let it rotate freely and hang it, it will rotate until its center of gravity is along the line it is hanging. That's always the case. So then I can say, okay, center of gravity is somewhere around here, along this line. It rotates until that happens because we have gravity down, weight, right, mg. And it will apply a torque to it in this direction, which is clockwise, negative. I can calculate it actually by finding the perpendicular component. If I know that angle, right, which is phi. If I know that distance, which is r, extending that, finding that angle. Remember, similar ideas. For torque, I can calculate that. And this torque, gravitational torque, causes to rotate until the center of gravity is along the line it is hanging. Using that idea, we can find center of gravity of other objects. But for most geometrical objects, center of gravity is in their symmetrical center, a regular geometrical center. Here is for square, rectangle would be the same, for a triangle, disk, and an empty disk, and so on. For an irregular object, we can hang it from different points, draw lines passing from there. For example, for this triangle, if I hang it from here, it will hang this way, draw a line, hang it from here, it will hang that way, draw a line, and the third, where those line intersects would give me an overall good idea of where the center of gravity for this guy is. But we will often use geometrical objects, and we will know the center of gravity is in the center, and we'll show the weight right in there. So these are the direction of mg. We've been already kind of doing this without a explicitly saying applying the mg to the center of objects overall. Here's an example of that. Calculating the torque due to gravity is exactly the same as calculating regular torque, only we are now looking at gravitational force or weight or mg, right? And then looking at how it applies a torque to an object. This question is says 3.2 kilogram flagpole extends from a wall at an angle 25 degrees from the horizontal. That would be this angle here. Its center of gravity is 1.6 meters from the point where the pole is attached to the wall, and it is also shown here. This is the center of gravity. Now notice here, folks, the center of gravity for this flagpole is not in this geometrical center because it's not a uniform object. There is a heavier part here, and it's generally closer to the heavier part. We know this by logic. We'll talk about more on when we get to equilibrium, rotational equilibrium. We can calculate that using torque of different parts of the object. But for now, we know that center of gravity is here, so we hang the weight there. Mg is right there. This angle is given as 25 degrees. R is given as 1.6 meters. All right. What is the gravitational torque on the flagpole? About the point of attachment. So pivot point is also given to us. I show my weight already, mg. I will need the angle between r and that weight, which is this angle here. Again, I have 25 here. This guy is 90 degrees. Same idea. Total is 180. So theta plus my phi is 90. So 90 minus this theta will be my phi. I can put it here as an equation. I kind of took a shortcut here. Is 90 minus theta is equal phi. I hope you guys are fine with these Greek letters by now. Phi is a new one for us, but we know theta, right? So I'm going to go ahead, find F perpendicular, weight times sine of that angle. Here, this would be the F perpendicular. And input it in here, R times F perpendicular, which is torque, right? Tau is torque, which is another new Greek letter we have here. Or I can just say RF perpendicular, or which is R times the force mg times sine. Well, this should be phi here, not theta. Sorry about that. But the solution should be correct. I used angle 65, which is phi here. And the answer is 45.47 Newton meters. Please make sure you solve this, understand it, and get the same number. So that's about what force is, what torque is. For stability analysis, we all know that how we should put things in the stability, and without realizing that we actually base the center of gravity of the object passing through its stable points, meaning that if I draw a line, it could be that there are two stable points. It's passing right in the middle of that. Then my car is stable. If I tip it over a little bit, that's not gonna be the case. Now it has only one pivot point, not 2 points stable. So if the center of gravity line is passing through here, it would be stable and not tip. But it's obvious that gravity will apply a torque in this direction and the car will tip back over. Tip it a little bit more, you can find a point where the center of gravitational line is passing through the one pivot point here, and you can stable the car like that. But if it tips a little bit to the left or right, it will tip over that right. So if you tip it a little bit more to the right, it will tip over this way, because now the center of gravity line is passing from the right, not from the pivot point here. It will apply a clockwise torque. Here it will apply a counterclockwise torque. Same goes for a human. If we are staying on our feet, we are nice and stable because we have two stationary points, and overall our center of gravity line passing through our feet. If we tiptoe, we break that. If we try to stay straight when we tiptoe, we will fall backwards, which is why we lean forward a little bit to maintain our balance and make sure that the line of gravitational force applied to us, or center of gravity line, is passing through our pivot point, which is the tip of our feet now. Now try this. If you stand in front of a wall facing it 2 feet down, you'll be fine. But if you try to tiptoe, the wall will prevent you from leaning forward a little bit and you'll fall backward, because your center of gravity line is not along your tiptoe. You would want to move backward to stay tiptoed, or you'll just fall backward. Try that. This is the same idea, and a conceptual question. What would be the tipping point for the man if he's painting a wall and leaning towards left, trying to reach a point? You would find an overall center of gravity of the man and the ladder system. If it's along this line, when you draw the line, if it's passing through here at least, which would be the tipping point. So this would be the pivot point, right? If the man falls over. And that would be a torque in this direction. If he moves the center of gravity a little bit out of this, here for example, he will tip over. This is a fun activity you folks may try. If you try to balance a soda can empty or full, it will not balance, because it will never be possible to have a case where center of gravity going through this point here. What balancing means, or balancing on one side of it. If you put it right on regular on both sides, of course it will be balanced. This is like a regular simple stable balance. But if you tip it on the side and if it's full, always the center of gravity will be somewhere here and it will tip it over. It will not be possible, empty or totally full. But if you put just enough amount of water to maintain that its center of gravity is a little bit down, you can make it stay this way without tipping. If its center of gravity, C of G, line is passing through this point, which would be the pivot point. Try it. I'll see you in the next video.